Okay, all right. Hope everyone's doing well. There's quite a few exams left for everybody, and I just had the win to actually do this. I haven't actually taught this course before, but I've taught a fair bit of the original Extension 2 course. There's only been 3 years of exams so far. This is the 4th iteration, the 4th time they've tried to write a paper with the new syllabus, which admittedly is a little bit bare in terms of details. So what we're going to do is we're going to start the timer and give ourselves 10 minutes reading time, followed by 3 hours of writing time. I'll try to write neatly so that if you're watching down the future, you might sort of learn from the insights. If you're a student of the future cohorts, please really have a go at this exam yourself rather than have someone spoil it for you the first time. You get so much more benefit from engaging with the paper on your own rather than sort of having someone explain it to you first. It's sort of like opening a Christmas present, assuming that you like maths. We're all here because we like maths, because it's Extension 2 maths, and you wouldn't be doing this if you don't like maths. So we're just going to quickly pop up the timer. We're going to start ourselves at 7:33 and finish at, gosh, I have to actually figure out how to do this, 7:33, and we're going to end at 10:43. So those are the times, start and end times. And yeah, away we go. Let's have a go at this exam. So we've already started our 10 minutes reading time. I have a little flick through, see what's going on with these. I think us teachers are not sometimes sympathetic enough to people doing these papers, because after all, like we're just there to tell you about the course, but when we actually have to do it, we're probably a bit rusty. So, okay, this one looks a bit like just an expansion. We'll move on. I do like to check the multiple choice just to start with, but I know that you should also browse the paper to see the kind of topics and in those 10 minutes. Okay, so this is some sort of converse issue. We'll deal with that when we actually attempt the question. Complex number here, bit of for all, there exists. Okay, whatever. We'll have to actually do the question. So you don't want to dwell too long on the first 10 minutes just to attempt these multiple choice questions in your head. And the reason behind that is that each question draws from such a different part of the course that if you end up getting bogged down with one question, there goes your reading time. So, okay, we've got a quick vectors question here. Okay, we'll deal with that when we get to it. Does not describe simple harmonic motion. Okay, do they still do that in the new course? Which of the following statements about complex numbers is true? This looks like an essay, honestly. Like the options already look quite complicated, so who knows? Okay, this looks like the old syllabus question. I love how they change the font whenever they want to do vectors. The Extension 1 course loves to use a little arrow on the top, like in 2022. Now they use bold letters. Great. Oh, now they use squigglies. Okay. Particle travels along a curve from O to E in the xy plane. The position vector of... Oh, right. I'm not sure where this is going. Well, yeah. These multiple choice questions are sometimes just going to be a blind guess for most people, probably including myself, but that's how it goes. And consider any three-dimensional vectors satisfy these conditions. I hate this. This looks like, that question last year in the HSC, in the Extension 2 HSC. And especially when they give all these options that draw on something theoretical. Not a fan. We'll see how that goes down. Okay, question 11. Let's see if there's anything unusual in 11. Hopefully not. Generally, it doesn't happen. Angle between the vectors. Okay, that can't go badly. Yep. By considering vector AB, show that that's also a parallelogram. Oh, wow, interesting. That's 2 marks to actually draw a diagram and prove something. Okay, fine. Particle moves in a simple harmonic motion. So clearly they still teach simple harmonic motion. That used to be Extension 1. Okay. And that's 4 marks of unscaffolded partial fractions. Now we are on question 12. Okay, so standard proof. Anyone that's done the course should be able to do this one. It's like sort of 3 marks. If you studied a little bit, you know, you do the marks, you get some scaling, then everyone wins, right? Prove. Okay, some inequality. We'll be right with that. Okay, some sloped. Now this is a point of contention because this gets examined in extension 2, which means in extension 1 it probably wouldn't get examined. You know, and it's kind of debatable what part of the course. Cambridge has put this in extension 1, but extension 2, you know, it's who knows like which course it actually belongs to. Got some standard polynomials and cube roots of a complex number. Okay, we have some, you know, general integration. Show that I've seen this in the old HSC course. This has been around before. This is actually one of the last questions of a paper in the early 2000s. I'm thinking like 2001, but there was like this exact quadratic inside of a square root sign in 2001, but I can't remember so well anymore. We'll see what they want out of this question. We'll see how we go. Question 13 there. Okay, let's see. 13C. So this is about nearly halfway through the written sections. Okay, initial velocity of the particle is this. So this is projectile motion, but something else is going on here, and I don't really know what part of the course that comes from. So we'll have to, like, you know, play it by ear when we actually attempt this. Hopefully you can just go with the flow. And the graphs, okay, great. Graphs are given in the diagram below. Find the horizontal range of the, range of the particle. Why is it that they gave you this diagram to talk about a motion question? Who knows, anyone's guess. Okay, question 14. How are we going for reading time? We still have about 5 minutes reading time, 4 minutes reading time. Okay, so these things hopefully are, you know, people are well trained to do these in terms of students, so it doesn't look too bad. A little bit tedious, but that's what they are. Another simple harmonic motion for 3 marks. Okay, well, we'll see what happens there. Now we have a resisted motion question, which was covered quite extensively in the old syllabus. So I would say that students are generally quite well prepared for these, and we'll see how everyone sort of goes in that one. We haven't actually seen that much of the new syllabus. Not much in terms of methods of proof, you know, logic, sentences, and all that sort of thing. Okay, we got this is great. You want reduction formulae in your question 15s and 16s because these are marks that anyone who's had some practice can access and have a decent go at. So, you know, yeah, that one's quite doable. And they have another reduction formula here. So that's 9 marks worth of reduction formula. And I like how they use J. It's almost like they're just copying from the old syllabus. Now, this question. Okay, so we got to be aware of the fact that it's a 3D diagram because it's a pyramid and some stuff is going on, and they have some lovely, okay, prove this for 3 marks. And you think, okay, 3 marks, that sounds really awful, but maybe because it's vectors, there is something elegant that you can do to get these 3 marks. You know, it's not going to be just bashing your way around the diagram. So we're going to have a go at that, and we look forward to getting up to this point. Hopefully within the 3 hours. We'll see how we go. Okay, we're going to go a bit low on reading time. A curve, L, spirals 3 times around the sphere, centered at origin. The particle is initially at the point and moves along the curve. Okay, surface ending at there. Using the diagram below, which shows the graphs of the functions, and considering the graph of their product, give a set of parametric equations that describe the curve L. Or is that C? I can't really read that. The graph of y equals f of x, g of x. Really? This is something that I haven't done before, so it'll be very interesting to have a go at this. Like, how do you teach people to do this question? Because parametrics, yeah, sure, but why is it that they're multiplying, and what's this supposed to do to help you find the parametric of the spiral? Okay, so we'll see how that goes. Let W be the complex number. All right, this is giveaway. This is all sort of, okay, look, I would say that this is hopefully accessible as a complex number question with cube roots of unity. So that's a good thing. You want old syllabus topics that people, are familiar with in question 16. Now, so far that's 6 marks in 16, and there's only 14 marks in total, which is unusual. They try to make 15 marks, but recently they haven't done that anymore. And in 16, the last question is made up of 8 marks consisting of some kind of, okay, 5 marks of proof, and another 3 marks of complex number. We know what happened with last year's complex number. They made a question that wasn't very good. At least I didn't think it was very good. So we'll see how this one goes. So there's our reading time. We're about to start writing. Now, obviously, you might receive advice from teachers, other peers to try doing the written parts first. But you know what? We're going to, just for the sake of continuity, attempt the multiple choice first in order of the exam. Okay? So what I'll do, my recommendation when you're trying to do multiple choice is you scribble your working on the question itself, and then hopefully you sort of see what's going on. So we got this. We're about to start our writing time. Here we go. Okay. So we've got the I cubed for the B term, which gives us, minus I, and it's either C or D. And then for the second term, we just have to differentiate the term that's of the I squared. So we got the A3 and 3A times IB squared. And this is the term that gives us minus. So we'll pick C for question 1. Okay. I don't know, like, as a non-student, we sometimes second guess ourselves because we're not really warmed up. That's maybe the reason why people do question 11 and 12 first. Okay, converse of this statement. If an animal is a herbivore, then it does not eat meat. Do they want the converse? Okay, so the converse would be, see, the thing is, like, when you have the converse, all you really do is just put an if in front of the second statement and then put then in front of the first phrase, and that's it. There's no, like, negation or anything funny. Luckily, with implication and negation, that is one of the poorly defined parts of the syllabus. So if the animal, really? Converse. I would say that if it does not eat meat, then it is a herbivore. Oh, it is there. All right, it's there. I just got completely bamboozled by the first two, options there, and I just thought, are they really doing negation? I really hope not. Okay, so that's D there. It's fine. Just put an if in front of the second clause, and put then in front of the first bit. Great. A complex number lies on the unit circle in the complex plane as shown in a diagram, which the following number is equal to Z bar. Oh wow, so, whoa, okay. That's kind of annoying. We've got Z, which equals to 1 cos plus I sine of, negative 2 pi on 3. So we know that Z bar is going to be cos plus I sine of 2 pi on 3. We know it's up there somewhere. But what are these options? Definitely not that one, because that one goes up there. Z squared, I'm kind of we're vibing this. I think that one would get you to the correct location. So we can stop looking and just say it's B. Okay, there it is, it's B. 4, considering which are the following statement about real numbers. Whichever positive number R you pick, it is possible to find a number x greater than 1 such that this. Okay. When this statement is written in the formal language of proof, which of the following is obtained? Well, whichever positive number means for all are greater than 0, it is possible means there exists. So we're sort of more and more looking at this one, and it's definitely C. Okay, so far we've got a pretty calm sort of start to the multiple choice, nothing too crazy. Which of the following is a true statement about the lines, these things? Yeah. Are they the same line course? Then, well, I mean, they could be the same line actually. So the way to do these sort of vector equation of a line is to try to like check the slope, and you can see the gradients of these two are sort of opposite each other. We're talking about the gradient vector, these two. They are the same gradient. So what is going to be annoying is to just verify whether they're the same line. They're definitely parallel, so it's either this or that they're the same line. So B and D are definitely out. Okay? Oh, my pencil broke. I didn't want to write on this with pen just in case someone else wants the copy of this. And but how do we prove it's the same line or not? Well, the way I do this is I'm trying to make this value, the x value of the first line 0, and to do that I want to pick lambda to be maybe a -1. Okay, so if lambda was -1 on this particular graph, L1 is going to turn into 0, -1, 4. Okay, now let's try to make this 0. So we're going to make mu -2, and what we're going to do, the L2 is going to give us a point of 0 as well. Now, putting 2 here, we're going to get 6. 10 plus 6 is not, so it's -4, and then putting a -2 there is going to give you a 3. I mean, well, clearly they pass through different points, so I'm going to go with C, but I'm a little bit shaky. I believe in my approach, but I mean, it has to be so specific if they do meet, you know, if they are the same line, they must have a common point when x equals 0, and in this case, it's not. Yeah, something's a bit unsettling about this, but I'm going to stick with C for now. Which of the following functions does not describe simple harmonic motion? Okay, so we know that when you have this has a cos 2t involved, so you can convert that into auxiliary angles. That is a simple harmonic motion. Out of these guys, auxiliaries involve simple harmonic motion. This one, if you just, you know, compound angle, look, we know that the periods are the same, so eventually they will add to another trig function that's quite simple. But I'm just checking something. Look, I don't vibe this. I just think that is also simple harmonic. It's just looking a little bit scary because of the shifting that's happened to these. But we know that, you know, if you're a physics student, you know that two graphs with the same period, even if they're different amplitude, as long as they're the same period, we'll be able to combine, right, into a different what's it called, thing of the same period. So the only thing that's really bad is this one. So I'm going to pick B. But again, 5 and 6 are like questions where I'm sort of starting to go, I can't guarantee a mark in these, but I think I'm pretty sure. You can't sort of dwell any more on it. You just have to keep going. Question 7. Which of the following statements about complex numbers is true? Okay, that's a lot of options. I'm not a fan of these types of questions when they give you like 4 theoretical choices. For all real numbers, with x not equals to 0, tan equals y over x implies this. Why is it implies? I don't even know what the point of this is. For all non-zero complex numbers, okay, if you have the two arguments, then the argument of their product is, well, I mean, that sounds harmless. I can't think of any time when it's not. But you see that there's the catch here is the principal argument. If you get two principal arguments, and principal argument refers to this, I mean, it's probably like that bracket, isn't it? And if you add them, Is it still the principal argument? A bit sus. I actually think it's a trap. It's a massive trap. They almost got us. Okay, so maybe not that one. 7C. For all real numbers, let's see, R1, yeah, implies that if you have two complex numbers equal, then their moduli are equal and their arguments are equal. I mean, come on, that's another trap. Like, these things could be a whole sort of multiple of revolutions apart, and these two complex numbers can still be equal. So the implication is just off on this one. And I mean, I can start to appreciate what they're trying to do here. They're trying to go, oh yeah, like if you have an imply, it means that this is a this is a sufficient condition for that, which is not true. You can't have those two. Those angles are not always equal. So what about this one? With r is greater than 0, okay, well, I mean, they should be anyway, and x is not equals to 0, for all real numbers x, y, this, yeah, implies for all real numbers. Yeah, but buddy, this has a range of minus 90 to 90. So how? Like, how can that be true if theta can be any real numbers? Something just, like, we narrowed it down to A, but I don't even know what A is trying to say. Like, how? And right now, we're about 10 minutes into the multiple choice, and I'm feeling like this question alone has bogged me down. For all real numbers x, y, theta with x not equals to 0. X, y, theta. Look, frankly, the way I think about it is that if tan theta equals y on x, it just simply means that theta has the freedom to be any real number, because it's just, except obviously the discontinuities of tan. And, and this is like no restrictions either. So this whole question has just been this convoluted thing about what the angle, the arguments can be restricted to. And it's like, I mean, what a tautology. What is this? This is one of those like questions where I think they should have rethought about what the intention of the question was, because this looked so meaningless to me that I didn't really want, I had to look at the rest of it to see something different, okay? And the fact that I had to falsify each one really shows me that this is such a vacuous statement. I think they equivalence. There's obviously, it's either equivalent or that theta and that theta, like, they have nothing to do with each other. Like, tan theta is just some random angle with some random numbers. What's it got to do with some complex numbers? Like, why is this even there, right? So anyway, we got to move on. We can't start ranting in the middle of a paper. Okay, question 8. Shaded arc and diagram. Well, we can do this. This one's not too bad, hopefully. Oh no, why is there a 2 there? Okay, so obviously the distance from I, which is here, is about twice the distance from 1, which is there. And as you can see, what's that mean? I'd rather not have to do the algebra all over this, but I'm going to take the word for it that this equals to this is the equation of the circle without going through all the algebra, okay? And therefore, we're saying that the distance from 1 is it greater than 2 times the distance from I. So let's try this. Let's try. So we know that the distance from here to 1. I'm not seeing this. What is going on here? Why is this circle even like that? Let's pick a more innocent point here. Let's go here. Distance to 1 versus distance to I. Yeah, alright. What? Yeah, no, that point is just such a distractor. Like, we really shouldn't be looking at that point. We're doing 1 and I, and clearly the distance to 1 is about twice the distance to I. So we know we can get rid of these. The distance to 1 is twice the distance to I. We've also got some other stuff going on. Is it greater? Well, if you pick a point all the way out here, we know that in that sort of location, the distance to 1 is certainly smaller than the distance to I. So, well, 2 times the distance to I. I mean, that itself is quite a long distance to I. So, I would say D will be the right pick because we are just sort of hypothetically doing it. If you wanted to feel safe about this, you can test 0 as well. 0, 0, I think that's the way I used to teach it. And that's the modulus of 1 is definitely less than twice the modulus of I. So that's definitely D. So that was quite a safe question. I'm happy with it. Okay, question 9. A particle travels along a curve from O to E in the xy plane. That worried me the first time I saw it, as shown in the diagram. The position vector of the particle is R. Sure. It's a 2D. Fine. And its velocity and acceleration is alpha. When traveling, the particle is always slowing down. Slowing down, I don't even know what that's talking about. What the following is consistent with the motion of the particle? I have no idea what this is testing. I mean, I might have to like hard pass on this one. What is this? What topic is this from? Like, what? And we're like almost 15 minutes into the multiple choice, and I'm not vibing this anymore. So we're gonna actually just pause on question 9. I'll come back to this if I have time. I'm not sure I will. This is alien language here. But then the stubborn part of me wants to keep having a go at this one. Okay, we'll just have a quick cursory glance, right? The position vector is R, and we're saying it's always slowing down. And we're saying the velocity vector Okay. I'm just going to draw you what I think the position vector of R is. This is the position vector of R. This is the tangential velocity vector of R. And as you can see, because it's always sort of going roughly in the same direction, we know that R dot V, based on vector notation, is their magnitudes multiplied by cos of the angle between them. And we know the angle between them is less than 90. So it's definitely positive. I'm going to go with C or D. And we also know that it's slowing down, which means that A has to somehow oppose the direction of the velocity, which means the angle between them, right, between velocity vector and the acceleration vector, is less than 0 because the angle, let's call this beta, is greater than 90 degrees. So I'm going to pick D. Look, it's not too bad, but it's such a vague looking question. Whatever, okay? So question 10. Consider any three-dimensional vectors, blah, 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 that satisfy these conditions. Okay? So their dot products are 1, 2, and 3. Which of the statements about the vectors is true? Could be unit vectors? I mean, if 2 of them are unit vectors, let's say these 2 are unit vectors. I don't get what they're trying to say here. What's it got to do with the dot product in the first place? The 3 points could lie on a sphere centered at O. What's this got to do with anything? For three-dimensional vectors A, B, and C can also be found so that those 3 satisfy these 3 conditions. Okay, fine. For all of these, there exists Rs and T such that R, S, and T are positive real numbers, and this is equal to what? We're coming back to question 10. I'm over it. I think this one requires some kind of brilliant insight. We're going to come back to it. So far, what we've done is we've picked our multiple choice answers, and I'm going to start on the iPad and actually write down all the answers I've had so far. So we're going to the overlay 2, and we're going to attempt the rest of the paper now. Okay. So my multiple choice answers are You know what? We don't really need to write the question numbers. We have C, D, B, C, C, and then from 6 we have B, A, D, D, and a question mark on question 10. We'll get back to question 10 later. All right, so let's try working our way through question 11 now. Question 11. Solve the quadratic. Answer in Cartesian form. I mean, at what point do you think they actually deduct marks? I'm sure all this is totally fine. Okay, we'll leave it there. B. Find the angle between the vectors. So and that here is a root 14. And that here is a root 21. So we know the dot product. Just doing the dot product real quickly is a, look, I mean, you don't really have to show the substitution step, and I'm doing this out of a sense of like, what would the marker award 4 marks for? And honestly, if you don't make a mistake, it's fine. If you think you'll make a mistake, write the substitution step. You know what, we'll write it just for the sake of people who might be watching this in the future. Okay, so we've got -1 plus 8 minus 6 equals to 1. Okay, and that 1 should equals to root 14, root 21, cos theta. And here we have that's a 7, root 6. I'm going to go get my calculator. I do miss these calculators from the previous iteration of Casio because the buttons feel so much nicer. Okay, so we're going to do shift cos of 1 on 7 root 6. And to the nearest degree, that will be 87 degrees. Okay, I hope I didn't make any mistakes. It makes me sort of nervous because for people who are practicing and getting ready for the HSC, they're probably more accurate than I am. So, well, what gives? I just double checked it visually. It looks fine. Okay, moving on to C. Find a vector equation of the line through the points. Okay, so when you want to find the vector equation, what you want to do is find sort of a sense of the gradient. And I don't have the reference sheet on me, but we'll just find. Okay, so vector AB. And that's going to be 3, 1, minus 2. And then the vector equation will simply be using one of those points. So we can say, I really need to learn my what's called notation. We'll just take point A as our sort of starting point. We'll put lambda multiplied by the gradient vector that we just found. Direction vector, that's what they call it in the new syllabus, don't they? Direction vector. Sheesh. Okay, question D. The quadrilaterals are parallelograms. Well, we need to draw this, don't we? Love the iPad. A, B, C, and D. And A, B, E, F. That's an awkward place to put A, B, isn't it? We'll try that again. C, D, A, B, and we'll put EF over down here. Not the best parallelogram. A, B, E, F. Okay, by considering vector AB, show that CDFE is also, I mean, really? Okay, so how much reasoning is needed to prove this? So we say basically that AB is equals to vector CD, because by definition of a parallelogram, have parallel and equal opposite sides. Similarly, we can say that AB, vector AB, is also equal to vector FE. Therefore, vector CD is equal to vector FE, and the sufficient condition for a parallelogram, for something to be a parallelogram, is simply that CD, this implies that CD is parallel to FE, and also the length CD is equal to FE, therefore CDFE is a parallelogram. You know, honestly, it should be, yeah, it's CDFE in that order. I feel like I wrote this in the wrong order. Let's just write, I would say AB is DC, but I don't really know if that's going to be bad for our marking anyway. Okay. I think they're going to be pretty generous with this reasoning. E. Particle moves in simple harmonic motion described by this find the period of the central point of motion. I don't really know how they teach this in the new syllabus, but in the old one, people used to memorize these kinds of formulas. It's been a while since I've done this. X double dot, we know it's going to be minus n squared x minus the center. And I feel like that's all they need, right? I can't remember this anymore. D half v squared dx. Is that? No. That's ridiculous. What am I doing here? This is the definition of the simple harmonic motion, the differential equation actually. So n equals to 3, and the center is 4. Is that all they wanted? Okay, so period equals to 2 pi on 3. Talk about free marks. Didn't have to integrate, didn't have to do any weird stuff. F. Okay, find the partial fractions. And this is a 4-mark question. So clearly they expect some process as to how you get the partial fractions. We have a over x plus 1 plus b over x minus 3, and all that should equals to 5x minus 3 over the 2 brackets. Therefore a x minus 3 plus b x plus 1 equals to 5x minus 3. So you let x equals to 3, we have 4b equals to 12. X equals minus 1, we have minus 4a equals to minus 8, and a equals to 2. So we have the following, oh great, they're giving us a definite integral as well. So 2 over x plus 1, and b is 3 over x minus 3. Okay, so 2 ln x plus 1 plus 3 ln x minus 3 from 0 to 2. This is the part of maths I enjoy least, evaluating integrals. Oh look, we have a negative as well. Now that bothers me a little bit. Do you know why it bothers me a little bit? I mean, we can always engage the absolute value and move on with life, but a part of me says, have they thought about this when they wrote the question? What we're really finding here in this integral is the fact that we're finding a graph that has vertical discontinuities at 3 and minus 1. Okay, and we're going from 0 to 2. That should be okay, shouldn't it? Okay, so I'm reassured that there is no discontinuities in this integral. That's great. So the absolute value should do the trick. Unless I made a big mistake on these on these A and B values. Now I'm worried about the A and the B. Let's just check that real quickly. Surely I've done something wrong here. Is this paranoia? I think we sort of starting to catch some sort of paranoia here. This is fine, okay? I just got sort of like spooked by this absolute value, but I think it all worked out. And in the end, the answer is 2 ln 3 minus 3 ln 3, which is negative ln 3. Great. We don't want to be losing marks on question 11. Okay. We're up to question 12. Prove that square root of 23 is irrational. Okay, so you assume square root of 23 equals to p over q, where p and q has a GCD of 1, as in they're relatively prime, they do not have any common factors, and that's really important. So I don't know the notation that teachers commonly use for this, maybe GCD of p and q. Anyway, they do not have any common factors. This is a simplified fraction. Therefore, q root 23 equals to p, squaring both sides, q squared equals 23 equals to p squared. Therefore, 23 divides p squared. Therefore, 23 squared divides p squared, because 23 is a prime number, therefore the square of it divides by p squared. And then therefore, we can say p squared equals to 23 squared multiplied by another integer. Okay, so this is a perfectly acceptable kind of reasoning, because we're saying 23 is a prime number, and inside of a square number, each prime number must have at least 2 powers to make it an actual square number. All right, and therefore we can say that 23 q squared equals to 23 squared m. Dividing both sides by 23, we have q squared equals to 23m. Therefore, 23 also divides q squared. Therefore, 23 squared divides by q squared. What we found is that there's a p and q are both multiples of 23, which contradicts the assumption that p and q are of the lowest terms in the original rational number. Okay, and I think that should be enough. Look, if you want to play it safe, you can always sort of go, this part implies that 23 divides by p, and that implies that 23 divides by q. I just sort of sometimes think, what are the marking requirements for a really precise proof? Because some things that maybe a mathematician thinks is obvious, that 23 multiple divides q, I don't know. Is that obvious to the HSC marker? Anyone's guess. Okay. We have B, question 12b. That was a big waste of time. Prove that for all real numbers x and y, where x squared plus y squared not equals to 0, that just simply means that neither of them can, well, actually one of them can't be 0. We have this particular scenario. I'm not a big fan of these kinds of proofs. So what we're going to do is we're going to do some scrap working on the side, where we just have a little play around. Squared plus 2xy plus y squared is less than or equal to 2x squared plus 2y squared. And upon rearranging, we have the basic arithmetic geometry for two terms. Okay, and in this situation, I just wonder why they cared about the x squared plus y squared, but let's attempt to write the full proof. So we know that x minus y squared is greater than or equals 0, because that's just facts. Therefore, x squared minus 2xy plus y squared is greater than or equals 0. X squared plus y squared greater than or equals to 2xy. Now, having a quick look at the scrap work we did here, what we did was we added x squared plus y squared to both sides, which is something we're allowed to do, right? So by adding x squared plus y squared to both sides, we've now got 2x squared plus 2y squared is greater than or equals to 2xy plus x squared plus y squared, and that obviously is a factorizable. I don't know why. Oh yeah, it's because you can't divide both sides by 0, of course. X plus y squared, and here we've got 2x squared plus y squared. Now, the only reason that they told us that little condition is so that since x squared plus y squared is not equals to 0, we are allowed to divide both sides by a positive number. This is a positive number, so it's not a problem. And I don't think the marker's going to mind if you didn't say anything, but we might as well just say something. Okay, you're dividing both sides by a positive number. There's B, 12b, 12c. Object slides down a smooth inclined plane with velocity v, where t, okay, great. After the inclined plane makes an angle of theta with the horizontal, and as shown in the diagram, the normal reaction forces are, the acceleration due to gravity is g. What we will do is, as I'm reading through this, we'll go to the other overlay so you can have a look at my thought process around reading of the question. Okay. The normal reaction forces are, the acceleration due to gravity is g, okay, and no other forces acting on the object. What's this other thing? Oh, okay, they're using this as the key, as the orthogonal basis for this. Interesting. Blah blah blah. Vectors. Okay, so they clearly want us to be doing this particular approach for this question, which is absolutely fine. And I don't really like how they put that there, because that is not a force. That's a force. That's a force. That's just a resultant sort of velocity going downwards. And yet they sort of included that as part of the thing. So in your working, when you're doing this question, you're going to be trying to just focus on the forces acting on the object. So let's just draw it real quick. We've got theta, we've got the particle, we've got mg acting down upon it. I never realized that g is actually a vector. Interesting. It's just the acceleration due to gravity, g vector. Okay, that's new. I guess we can sort of live with that. There's r. Now what we have to do is separate the gravitational force into the following components. You've got that component and that component. And the angle here, theta, that's the complement of theta there, so that angle here must be theta, and we have those components. So that component is simply going to be mg. Why are they using, I don't understand why they need to actually use the vector symbol for the downwards gravity. Anyway, mg sine theta, and that component is mg cos theta, at least in terms of their magnitudes. We'll worry about I and j in a little bit later. Clearly, they've picked I as up the ramp and j as away from the ramp. So that's what we're going to use. So how do we show this? Okay, the resultant force on the object is that. Well, here's the thing. If you're trying to find the resultant force, you know that because the object is never going to fall through the surface, the vertical components, the j component, is never going to be a factor. So therefore, we're just treating this along the slope with up the slope as positive. And I think the diagram is all you really need to say. But let's just, give the resultant vector and give them some more reason to give us 2 marks. Okay, the resultant vector is minus mg sine theta I plus we've got rj, I'll put j at the front, as well as minus mg cos theta. As the object has no tendency to move perpendicular to the plane, the j part is equal to 0. Therefore, the resultant force, because they wanted the entire resultant force, so I can kind of see why they want a bit more working. We're just playing it safe here, not taking any chances with just saying, oh, look at the diagram, there's the resultant, and off we go, right? Just going to play it really safe, not just referring to the diagram here. Part 2. Given that the object is initially at rest, find its velocity in terms of g, velocity vector in terms of g, theta, t, and I. I mean, I don't really see the point of this, because there's nothing 2D about this anymore. Why don't we simply just go velocity equals to just the integral of the amount that's going down the ramp? I'm not sure if this question really captures the difficulty of this particular topic here. So C is 0, obviously. And you know what, we can even write vector notation if we really cared, but it doesn't really matter. And therefore, the velocity vector in terms of t is simply minus mg sine theta, okay, t. And you know what, we're going to slap on a vector I just to make people happy that this is a vector topic that shouldn't really be a vector topic. And I've said it. Vector is a tacked on topic that hasn't been fleshed out in the new HSC. There it is, boys. Okay. I don't see the point of these 4 marks. Maybe they're just there as gift marks to everybody. Anyway, question 12D. How are we going for time? We're about less than an hour in. I'm kind of getting tired as well. It's pretty late in the evening. Question 12D. Find the cube roots of 2 minus 2i. Now, for these kinds of questions, you have to have learned and practiced how to write 2 minus 2i in modulus argument form. 2 minus 2i. So it's this one, and we got the modulus being root 4 plus 4 is 8, root 8, and the argument is minus pi on 4. So we have 8 cos plus I sine, root 8 cos plus I sine minus pi on 4. And if you're one of these new age people, you write this, right? Because that's what the cool kids do now. They write it in Euler's form. Good on them. So let's attempt to solve it. We're saying that why don't we, just for my own novelty, I'm going to do this question in Euler's form because I have a feeling that's what the solution's like too. Okay, so we have r e I theta. We want that to be cubed to give us root 8 e I minus pi on 4. And then we say, okay, r cubed equals root 8, r equals to root 2. That's not a problem. We've also got 3 theta equals to minus pi on 4 plus multiples of 2 pi. When n equals 0, we have 3 theta equals to minus pi on 4, theta equals to minus pi on 12. N equals 1, 3 theta equals 2 pi minus pi on 4, which makes 7 pi on 4, because 8 pi on 4 is 2 pi. The theta equals to 7 pi on 12. N equals to 2, 3 theta equals, we have, I'm getting a bit tired for this. 2, we have 4 pi, 16 pi, so that's minus a quarter, 15 on 4. Theta equals to 15 pi on 12. It makes me nervous when things like get nicer, the fractions get nicer, like I don't know why, but here it is. So therefore, we have z equals to root 2 e to the I minus pi on 12, root 2 e to the I of 7 pi on 12, and root 2 e to the I of 15 pi on 12, which is dividing by, simplifying. I double checked my fraction simplifying one more time, and that's the 3. And they wanted an exponential form. Lovely. Okay, so that's what they wanted. We don't need to convert into Cartesian form. Fantastic. So E, 12e. The complex number blah is a 0 of the polynomial. Okay, great. So we got 2 plus I, and this is the conjugate root theorem about to occur. And we have P of z equals to z to the 4 minus 3z cubed plus cz squared plus dz minus 30. Explain why. All you have to say is that because the coefficients are real, and that's all that the markers are going to look for in your answer. Therefore, z bar, which equals to 2 minus I, if you want to really spell it out for them, is also a root. A 0. I think we're going to say 0 for this one. Yep. Good. And part 2. Find the remaining zeros of the polynomial. Now, because it's to the power of 4, we've got a fair bit to do there, especially because c and d isn't given. So we're going to try our best to use the minus 3 and the minus 30. So we're saying 3 over 1 equals to 2 plus I plus 2 minus I plus alpha plus beta, which are the other two roots. And just counting it out carefully, we've got minus, plus, minus, plus. So I'm just checking that again. So minus, plus, minus, plus. So we have minus 30 over I equals to 2 plus I, 2 minus I multiplied by alpha beta. So we just have to quickly simplify this. We have 4 plus 4. This leads us to 3 minus 4. Alpha plus beta equals to minus 1. And here this leads us to, why did I write an I there? That's bizarre. We have minus 30. We'll take our time with this part, just because 2, and then we have the I squared, which is minus 1. So we have 5 alpha beta. So we have alpha beta equals to minus 6. These things are quite tedious. I'm going to make alpha the subject. And usually when we start getting into year 9 and 10 maths, things can go quite wrong if you just lose one minus sign. What am I doing? I think I've replaced beta by 1 minus. Yep, just as I was talking about it. This is what happens. Kind of funny. We divide both sides by minus 1 just for the hell of it. Beta squared plus beta minus 6 equals 0, and therefore beta minus 2, beta plus 3 equals 0, and beta, and really what happens then is that one of the solutions will give you alpha and beta anyway. So beta equals to 2, which leads us to alpha equals to minus 3, or beta equals to 3 and alpha equals to minus 2. And I'm sure that that's going to work. So what are our roots? Have I done something funny? I'm just concerned, as long as there's no complex roots of this, then we're pretty happy, aren't we? Yeah, so this is fine. So therefore, the remaining zeros are 2, and minus 3. I was just sort of mentally checking if there's any issues with maybe another pair of complex roots, but alpha and beta did not lead to a quadratic that needed complex roots, thankfully. So that's great. Now we're up to question 13. Okay, so another integral. Another one of these fraction-looking integrals. We know that this integral, considering there's an x on the top, as well as an inverse sine-looking sort of object down the bottom, is going to be split up in a way that first deals with the minus x. And what we really should do is, for those of us that have done extension 1 or even advanced maths, you will be doing reverse chain rule because that is the flavor of the new HSC. So we have this, we have this. So we know that we'd like to target the numerator to have this on the numerator there. Okay, and so what we're going to do is put a multiple of 2 up to the numerator. So we have a 2 minus 2x over the same square root, and followed by adjusting the numerator so it's actually minus 4. So we have minus 2x minus 4 plus 4 to undo the minus 4, and plus 2 because that was there before. Okay, with the square root dx. And now just be really careful because you've got a half here, and that half applies to everything inside that integral. So we got this, and we've also got a half with a 6 on top of this. Okay, so this part will be quite quickly reverse chain rule, but just to play it safe, we're going to go minus 2x minus 4 followed by 5 minus 4x minus x squared. Gosh, I think I'm pretty rusty with my integration if I'm having to do all these steps. And over here, we're going to put 3 out the front because that's what we did with the 6. And okay. And here, there's lots of new approaches to doing this, but I think the way that I always preferred was to think, okay, what is it that I need to make a perfect square here on the bottom? So what I tend to do is start with a minus sign, maybe a 5 minus bracket x squared plus 4x. I've seen a better way to do this, but I've just never internalized it, and I just keep doing this, and I keep teaching it this way as well. I think the better way is to let u equals to x plus 2 or something, but I don't know, I'm always more comfortable with this. So we actually have a 9, and that's always a good sign, right? So we completed the square in line with the expression, and then we multiplied the minus sign with a minus 4 to combine the first term. So we have an x plus 2 inside the bracket squared there with a dx. And we're ready to integrate. So we have the f dash x disappearing in our integral, and we have 5 minus 4x minus x squared, add 1 to the power, divided by the new power. You know what, we'll play it safe and show that step there. And we have 3 inverse sine of x plus 2 over 3 plus c. And finally, we can tidy it up as a surd if we want to make it look a bit nicer. And that's not too bad. I'd say that just a bit of a chore to do. That's 13a. 13b. Show that. Now, these kind of show questions are always a little bit dubious because you have to waffle a little bit, and there are graphical arguments, and sometimes, I don't know, oh, they want if 4k is greater than or equals to 3. So why not RTP this? Now, we can always draw this. And this is always my first approach to these. And because it's so nicely factorizable, I'm a fan of just sketching it. Okay, so we're going to sketch the parabola real quickly. And we don't even need the y-axis because we have this. Is that a 3? Yeah, 3. Minus 1. We have a concave up parabola. And we can tell that in this particular domain, including the 3, this is clearly greater than or equals 0. So we can say from the graph, this expression I mean, really, you shouldn't be using any sort of discriminants or other arguments for this. Just this is adequate because it's a 1 marker, right? No, please don't do induction because k is real numbers, not integers. Okay. Part 2. Hence or otherwise, use mathematical induction to prove this. So now we have to do an induction question. Okay, so case 1. So look, I know that the new induction sort of textbooks and all that really like to show the base case by say proposition for n equals 3. Why don't we write that? Proposition for n equals 3 is, I hate this, I can't do this, I'm not doing this. We'll just say let n equals 3. I don't think the marker's going to care either way. Okay, left hand side equals to 2 to the 3, which is 8. Right hand side equals to is it 3? Yeah, 3 squared minus 2, which equals 7. Fantastic, so we got that, and therefore left hand side is greater than, well, I mean in this case it's greater than the right hand side, but greater than or equals to is true as well. Okay, so that's fine. Assume that for n equals to k, where k is greater than or equals to 3, this is really important. This is what is going to help you sort of use that statement that you've just proven in the earlier part, in part 1. So assume for n equals k, and k is greater than 3, that this inequality holds. And we're trying to prove that for n equals to k plus 1, that 2 to the k plus 1 is greater than or equals to k squared minus 2. Oh, no, what am I writing up? Why am I just autopilot writing the same thing again? K plus 1 minus 2. That's a 1 there. Okay. So how do we go about doing this? We start from the left-hand side. Left-hand side is equals to 2 to the k plus 1. But we know from the assumption that this is greater than or equals to 2 times k squared minus 2. Okay, so, and if we continue to sort of equate this and simplify it, we've got 2k squared minus 4. So what we're really doing at this point, and so you can have a little pit stop here, you can say, what we really would like to prove is that 2k squared minus 4 is greater than or equals to k plus 1 all squared minus 2. This is our goal, okay? So what we can do is we can say consider. So sometimes when you have these inequalities where you can't really see the connection between the two sides and you can't really prove you can't really make the statement that you're trying to prove, you say consider the function 2k squared minus 4 minus bracket k plus 1 squared minus 2. So we're just going to consider this expression and expand and simplify that. Minusing the k squared, we have a there's just a single 2k there. We have minus 4 plus 1. I'm a bit suspicious about this. Why did I write plus 5? It's more like minus 3. That's a minus 3, which we know is greater than or equals to 0 for k is greater than or equals to 3, right? So therefore 2k squared minus 4 minus this whole lot is greater than or equal to 0, because these things are all the same. And therefore 2k squared minus 4 is greater than or equals to k plus 1 all squared minus 2. And now we can offer a continuation of the previous left-hand side. Therefore 2 to the k plus 1 is greater than or equals to. Where are we even at now? Yeah, well, I mean, obviously that was the largest, so we've now managed to prove it, and we can say statement true by mathematical induction. Okay, so as you can see, we had to do a little detour here to stuff around a little bit with the comparison between 2k squared minus 4 and the right hand side, which is k plus 1 squared minus 2, after doing the initial assumption inequality to turn the exponential into a quadratic. Great. That was 13 part B. Now, just having a look at the time that we spent here. Oh, thank you, Joshua. I missed your message. I was so engrossed in looking at the paper. I have to say, you know, just even as a teacher, it's quite time pressuring to do these exams, sort of, yeah, under exam conditions. Okay, so we're about an hour in, and we're up to about midway through 13. I don't know if that's good or not. Yeah, a bit over an hour in. Okay, question 13C. Good luck, Joshua, with your next exam, whatever that exam is. 13C. We're probably going to start getting onto the parts of the exam where the questions will get more and more difficult. Here, I'm going to refer back to the exam paper and have a read through this. Okay. A particle of mass 1 kilogram is projected from the origin with speed 40 meters per second. Okay, so yeah, well, I mean, that's a giveaway mark. Well, let's solve the context. The forces acting on the particle are gravity and air resistance. The air resistance is proportional to the velocity vector with a constant of proportionality 4. I've never seen questions asked in this way before, but I hope it works out nicely when we actually do it. Let the acceleration due to gravity be this. Okay. The position vector of the particle at time t seconds after the particle is projected is this. Show that vt is this. And then show that rt is this. Great. Look, I think with this question, we just have to go with the flow. There's not much, I don't think, in it. So, firstly, we write the projection velocity vector, which is speed 40 and 30 degrees to the horizontal. And really all you have to do is write those two components, and that is 40 sine theta, sine 30, which equals to a half, so that's 20. And here you got 40 cos 30, which equals 40 root 3 onto, which is 20 root 3. That took me a while to get out. Okay, and therefore the velocity vector at time 0 is 20. They wrote it in column form, so that's fine. Part 2. Show that the velocity as a function of time. So what's actually happening then is that according to Newton's second law, we need to actually have acceleration applying to the particle. And let's have a look at the acceleration applying to the particle. We've got an acceleration applying to the particle of something like this, of 4 times the velocity vector. Okay. I'm sort of like, I'm not that across the kind of style of question this is. I'm really winging this one, and it's it's interesting. It's interesting. And we've also got the gravitational vector, which is, 1 kilogram. Okay, so 10 going downwards this way. What I'm really concerned about is this v. Let's break it up into what is 20 root 3? E to the minus 4t. Where's that all come from? I'm going to assume that 4v, but it's minus, isn't it? Because it has to be minus. We have the x component of the velocity and the y component of the velocity. This is into like random winging it territory now. I've never seen this before. And therefore the overall acceleration resultant. How would you teach people this? Is minus 4 Vx we have a minus 10 on the vertical as well as a minus 4 Vy. You know what this all is that this is the cruelty of the new syllabus, is that it all really is just x components and y components, but written in such a sort of funny vector way, and that's what bugs people, right? Because if people didn't write it like this, if people wrote this like a proper projectile motion question, you're not going to have any problems, right? In fact, let me just show you what I mean by that. So if we decided to write this as x dot and write this as y dot, then everything should be fine, hopefully. Okay, so let's try it out now. I'm feeling positive about this the more I'm looking at this. So we're saying that d dt. I don't know. I'm kind of like, you know what? Let's continue with the dv. It's just a notation that bothers me so much. Okay, we can separate the variables. We integrate both sides. Frankly, I don't really know how easy it is to write this or what style of working they expect. And we know that there's a plus c, but initially when t equals 0, Vx equals to 20 root 3. I mean that is 3 marks, so we can't waste so much more time anymore. So ln 20 root 3 equals to minus 4t plus, what am I writing? That is c, that's just c. They're using e to the minus 4t, so we're going to keep the minus 4t to that side, and we have ln Vx over 20 root 3 using log laws for addition into minus 4t. Vx over 20 root 3 equals to e to the minus 4t, and therefore Vx equals to 20 root 3 e to the minus 4t. And we have to do all this again for the y values. Look, honestly, if we wrote this as just v, like the old syllabus, or if we wrote this as x dot, which might look a bit awkward because it's like the x double dot, x dot dot, so there's no comfortable way of writing this. I feel like v subscript x is the way that they probably want you to write it. Now we're going to have to do the other one really quickly. Don't tell me we have to do this. Ah, joy. Okay, so I feel like I'm preferring the 10 plus 4 Vy with a minus 1 on the dt here, with the separation variables like this. So we have a negative t. And here we have a quarter ln of absolute value 10 plus vy. Or is it 4vy? Yeah, 4vy. What a time waster. When t equals 0, vy equals to 20. So we have a quarter ln of 10 plus 80 equals to c. That's a 90. And we're going to move that over to the other side. So we have minus t equals to a quarter ln of absolute value of 10 plus 4 vy over 90. And we times the 4 back over. 10 plus 4 . And I'm going to assume everything's positive, so these absolute value signs don't need any more mincing around to justify with taking away the absolute value signs. What have they got here? That is disgusting. E to the minus 4t, my bad. Okay. As requested. We're really into unknown territory here. And yet we have 2 more marks of this to do? Oh gosh. Oh gosh, goodness me. So this was all part 2. This was all part 2 for 3 marks. I mean, it doesn't feel like a lot after we've done it, but that's a lot of work. And we're only on towards the end of 13. I'm not halfway through the exam yet. I've just spent 10 minutes doing this, easy, trivial looking question. And we're on the displacement part now, but hopefully that's easier. Okay, so we say, now we say the displacement, so we're going to use Rx, okay, but I think for this one, we can just integrate it wholesale. So let's go Rx. I'm just so bothered with the fact that we can't use the old x dot y dot notation for some reason, because of the fact that like x dot would mean, if you want to differentiate x dot, you'll be writing x double dot, and then you have y double dot there, and like, I know why. It's because we have to separate variables, and using x dot just looks really awkward. Is that it? Yeah, anyway, let's move past it. Let's get on with life, everyone. I'm just, what can I say? Rx, okay, the x component. That one should hopefully be, well, we know the velocity vector and it's in terms of t, so it should be simply the integral of the vx dt. We didn't even need separation variables for this one. So after integrating that, all right, let's calm back down. And when t equals 0, initially it's from the origin, so we have 0 equals to minus, so c is 5 root 3. The same thing for ry. We just have a function of t already. Should have simplified these earlier. They're using 45 on 2, and now they divided it by a further 2. So we have a 45 on 8 now, but negative. Minus 5 on 2 t plus c. When t equals 0, we have an r of y of 0 as well. So we have minus 45 on 8 times 1 plus c. c equals to 45 on 8. And it's cute, they factorized it. So r of y equals to 45 on 8 bracket 1 minus e to the minus 4t minus 5 on 2t as required. Oh, goodness me. Okay, so that's part 3. We have a part 4 of this question. Now I'm just going to go back to the page and talk about my thought process looking through at the 4th part of this question. So, having gone through that entire chore and having our brains tenderized by the meaningless integration with notation, terrible notation that has occurred. Maybe that's been going on in the past HSCs, but I just haven't done enough of the recent HSCs to know that this is a trend. We're going to try to answer the question. So, they've given us a function that resembles the thing in the bracket. They've also given us a linear graph for some unknown reason. And they're saying that x0, did they even say what x0 is? What is x0? I know 2.25 times 4 makes y equals 1. And why are they saying this? What's it got to do with anything? If I put 0, it's e to the minus now, which is also very close to 1. But why? Find the horizontal range of the particle, giving your answer correct to 1. What is this question? What is this question? Like, clearly the range is when r of t, right? When like y, the y value, r, the y component of the displacement vector equals 0. So clearly we just want this expression to equals 0. Okay, and when you attempt to solve it, if you are solving this, you will get 1 minus e to the minus 4t, and if you move that to the other side, you will, arrange the 45 and the 8 to get, 4x over 9, I'm pretty sure, right, 4 over 9t. So we know that they meet there. I mean, at least tell the student that this x0 is an intersection point, because, like, as far as we know, are they telling us maybe that's where it crosses the asymptote? Like, what is this x0? Spell it out for them, that it's an intersection point. Okay, so assuming that it is what they want, we can simply say r of y equals to 0, and therefore 45 on 8 upon solving. On 8. That's going to definitely have a 4 on 9 here. We know the solution to this according to the graph. This is like kind of advanced level stuff, where they give you an approximate solution by means of a blatant graph that don't even spell out for you what x0 is. The solution is approximately t is approximately 2.25. Okay, and therefore the range is going to be approximately as well the r of x value, which is 5 root 3 1 minus e to the minus 4 times 2.25. I'm just going to give it in exact terms because I'm not sure what they are looking for in this question anymore. E to the minus 9. And to me, that's very, very close to 1. So to round it to 1 decimal place, you know what? Let's entertain them. 5 root 3 1 minus e to the power of minus 9. One decimal place. 8.7. I want to say it's meters. Yeah, why not? Alright. That's frustrating enough. I think we've had enough of question 13. Let's carry on. So far, the time that we've used is an hour and roughly 20 minutes. We still have about an hour and 40 minutes left. Or is it an hour and 50 minutes left? An hour and... I don't know. An hour and 40 minutes have I stuffed up the way I count for time? I don't know anymore. It's an hour and 40 minutes. I'm just staring at the clock and I'm going, I've spent an hour and 30 minutes actually, almost an hour and 30 minutes. Okay, great. Starting to talk to myself now. Question 14. You see, we've only gone through half of the written question marks. The questions aren't getting easier, and we are nearly through half our writing time. So, and I really sympathise with people who've done the HSC in actual exam conditions, you know, who've been in an exam hall with all the stuff going on, the pressure of their HSC. Like, this is not good for your mental health, you know. I hope everyone has a good, relaxing time now that they've done their 4-unit exam. Hope 3 units good for you on Friday. Part 1. Okay, now we're back to complex numbers, hopefully familiar territory. I'm going to first sketch what I think about these. Okay, and we've got W is e to the I 3 pi on 4. I don't know why they gave it like this, but we're going to just go with what they asked us to write it in Cartesian form. So we have 1, these are all modulus 1, of cos pi on 6, which is going to be root 3 on 2, plus I sine pi on 6, which is going to be 1 on 2. I don't know how the Euler form, the exponential form, helps you with any of this. In the end, we still have to go to cos plus I sine. Okay, cos of 3 pi on 4 is minus 1 on root 2 in the second quadrant, and I sine of 3 pi on 4 is 1 on root 2. So we got these guys, and we're going to add them. So we got root 3 minus 1 on, no, they don't have the same denominator. Let's take a step back. I have this urge to write I with a little squiggle underneath it. Okay, wonderful. Something looks a bit suspicious to me, but I'm just going to leave it there. And they want the magnitude squared. So the magnitude squared is simply going to be that squared. That's a bit tedious for a question 14. A single mistake can just derail you. You got 3 on 4 minus, the 2 cancel out, so root 3 on root 2 plus 1 on 2 plus 1 on 4 plus 1 on root 2 plus 1 on 2. Just going through all that, we've got a whole 1 plus another 1, so we've got a 2. Yep. And we've got a third, which is minus root 6 on 2. And we've got another third, which is plus root 2 on 2. And making everything over 2, we got 4 minus root 6 plus root 2 on 2. I have to say, look, if after that last question, if you're really like strapped for marks, this is where you're getting the marks. So maybe this is like, you know, small mercies. The complex numbers are represented by the vectors respectively. Great. Show that the angle is this. Okay, now we know that the angle AOC, let's just quickly sketch this just to have an idea of what they look like. The first one is 30 degrees this way, and we're going to call this A. B is 135 degrees this way with the same modulus, and the sum is going to be the opposite of the parallelogram, so that's going to be that one. They're going to call it C. Okay. And they want to show that the angle AOC, so they want this angle. Interesting. Is that. I was originally looking at the vector of Z plus W, and I'm sort of like going into the vector mentality where I'm kind of going, oh, that's that multiplied by its what's that thing in extension 1? I can't believe it. Do you know what's crazy about all this? Is that if you're thinking in complex numbers, that stuff in my head about vectors what was that? No, that's just the dot product, A dot A. We don't need dot products here, do we? No, we don't. This is complex numbers, everyone. What is going on? Okay, so we want to show that this angle is 7 pi on 24. How do we do that? No, don't tell me. Don't tell me this is what I think it's going to be. No, 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 no. Oh, I have a bad feeling about this. Seven pi on 24. What's that got to do with any of this? Pi on 6. We have 3 pi on 4. So we have 3 pi on 4 minus. Is that it? I mean, I hope that's it. Like, we just have to simplify this, and it gets to be multiplied by 3, 9 pi on 12 minus 2 pi on 12, which equals to 7 pi on 12. So that tells us that this angle in between is 7 pi on 12. And because it's a rhombus, we know that diagonal OC bisects angle AOB, and therefore angle AOC equals half of that. I mean, you know, for a moment there, I was starting to think about like maybe going, oh, you know, like let's pretend this is a vector, and we're going to dot product it with itself, kind of like this, right? And then have z dot z magnitude of z squared plus 2z dot w. And then I realized, wait a minute, z dot w is not even relevant. I mean, that's the angle between the two vectors. We have much better ways to find it, considering we've got the arguments of both of them anyway. So that was some brain cells I did not need to engage just now. Oh well. Okay, part 3. Great. Deduce that, excuse me, cos of this is this. No, do not tell me. That is disgusting. Why would you ask this? Why would you ask this? You've got, I know what they went for, because you see, if I just switch to the question, like, and this is a skill. Oh no, I had this the whole time. Oh dear. Oh, I missed the fact that we were so tilted by the R question that we didn't go back to this page. Oh, funny. Okay. Going back to the question paper. Why would they do this? This expression looks awfully like twice, or is it half of that expression? Something about this just makes you think they look very similar. And in fact, you can tell that if you multiply the top by 2, but you also had a square root of it, there is a relation between these two things. And we know that the length of OC on our diagram, I'm just going to show you the diagram. So that whole time, if you were listening to my narration of how I got this question, you might have missed the fact of how I got 7 pi on 12. Okay, so I'm just going to redraw something. So we know this length from O to C is this nasty looking square root that we found earlier, and surely this is going to help us. We also know that the angle here, this is a length of 1, and that is a length of 1. We also know that this angle here is 7 pi on 24. So the question really comes back to a right-angled triangle with SOHCAHTOA, okay? Because we're saying that cos of 7 pi on 24 equals to half of that, so 4 minus root 6 plus root 2 divided by 2, right? Just because of all the sort of congruencies that you can get from this sort of bisecting of the rhombus, or half of the rhombus, right? You know this is that over 1. Okay, so this distance that I am referring to here is talking about half of the length of OC. And I think once we have this, is that not it? Or have I missed something? Why do they have a square root there? What is going on there? Oh, that's right. We forgot about the fact that oh dear. There is a square root there for the actual length of OC. My bad. I'm going to clean up this part, put a square root there. We're then going to cut it in half, and the hypotenuse is 1. That's better. So we have a square root of 4 minus root 6 plus root 2 over 2. I think that's right, that's the length. And that divided by 2 is kind of like multiplying it by a half, like this. And it seems like they got rid of the square root on the bottom for some reason, because they multiplied the top and bottom by root 2. They rationalized the denominator. Yep. So 8 minus 2 root 6 plus 2 root 2 over just a proper 2 now, times a half. And I think it's good time that we just crossed all this out and wrote a 4 in this place. And that is the answer. Should we tidy it up? Yeah, okay. Okay. That was why it's only worth 1 mark. Okay, so we're getting up to 14b, and time is ticking. So you can see how now each mark is taking us approximately a bit over a minute because we get bogged down thinking, and that's not a good thing. The point P is 4 meters to the right of origin on a straight line. Okay. The particle is released from rest at P and moves on a straight line simple harmonic motion with period 8 pi seconds. So we got 2 pi over n equals to 8 pi, leading us to have n equals to a quarter. Okay, this will come in handy later on. After 2 pi seconds, another particle is released from rest at P as well, and also moves along the straight line about O. What? About O. So they both sort of started there and did like some bouncy thing. Okay, because it says the center. When they mean about O, I really hope they mean O as the center. Yeah, I don't think it can mean anything else. After 2 pi seconds, yeah, find out when the two particles first collide. Okay. So what we're going to do is we're going to create the first particle's motion. And we know that because the particle initially begins at a 4 in the positive, we know that cos is the ideal graph for this. So it will be 4 cos with n, and with no constant term inside of the angle, because we should be okay. As you can see, when t equals 0, it will have the amplitude. We have the amplitude, we have the n value. We do not need a auxiliary angle, so that's great. The second particle, now this is actually a really important skill even for Extension 1 students. We also have 4, we also have cos, but because it's projected after 2 pi seconds, we are going to say that t minus 2 pi, because think of it this way, if you have at time t equals to 2 pi, this t refers to the time since when the first particle is projected. So at that moment, you should also be at the beginning of your motion of the second particle is at the beginning of its motion. So we're trying to find the first point of intersection of these graphs. And to do this, we're simply solving. Now, admittedly, this skill is something that I'd say the old syllabus students are probably stronger at. Trigonometry continues to be a deficiency in a lot of students' skill set. So what do I mean by that? Well, what we have here is we have a general solution to an equation, and my advice will be to make this the subject, so the right hand side's angle, and here we have a quarter t, but you see the thing is, it's not really a quarter t, but more the a 2n pi plus minus a quarter t, and we have to scout out some values for n. So let's say if n was 0. What does that give us? T minus 2 pi. Well, that gives us nothing. That gives us 2t equals to 2 pi, which equals to pi. Okay, that's a potential solution. Let's try n equals 1. What do we have here? We have t minus 2 pi equals to 8 pi plus t. None of these answers ever worked, the left-hand side answers, so that's not an issue anymore. And t minus 2 pi equals to 8 pi minus t, and that's 2t equals to 10 pi. That's a much later time. Just to be safe, let's try n equals minus 1, because we know that as we make n bigger, it'll just get worse. We know the first thing doesn't work, so let's try the other one. We have a quarter. Plus we know won't work, so we put a minus sign there. And I think this kind of feels a bit tedious. It probably is. And that's a negative time. So really the only legitimate time is this, and I think if you were a graphing kind of person, you would have achieved this answer straight away. Let's just do a quick test to make sure that pi actually works as the point of intersection as when their displacements are equal. So we have the first particle is a quarter pi, so cos pi just sounds too good to be true. I'm just a bit concerned about it actually. It can't be. It can't be, because it doesn't make sense. Like the second particle has not even started yet. Wow. So this is the one. This is the one. Good thing we went back and checked and didn't just pick the smallest number. Okay, so it says find when and where the two particles first collide. So let's answer the question. So when t equals to 5 pi, the location is going to be x equals to, what was it? 4 cos a quarter t times 5 pi. And that's 4 cos, look, we know where that is. That's in the third quadrant, and so on root 2. So at 2 root 2, was it units? To the left of the origin. Okay, that was okay. That was not too bad. Still took us quite a while. 14C. A projectile of mass m is launched vertically with the origin. Now this is definitely an old syllabus question. I think we can try to speed through it because we are running low on time. We need a solid hour and plus to do 15 and 16. You know this. So, initial speed v0. The projectile has resistive force, or K, capital M. They love the capital M, okay. Where K is a positive constant, V is the speed of projectile, the maximum height reached particle show that. So this is a very, very standard question. If you've learned any mechanics, this should not be a problem to you. So we just draw a little force diagram. As the particle is traveling up, right, we're going to say up is positive, and this is on the way up. We have two forces. We have the capital MG, and we also have the resistive force of K, capital M V squared. So I think all this is just going to be a bit of algebra. So acceleration equals to, well, let's net force, okay. And then acceleration is this. Well, let's just divide both sides by n. We don't really have to deal with m anymore. And as you can see, in this type of question, the appropriate thing to do is probably dv dt. And now that we've learned differential equations in extension 1, the preferred way that I think a lot of people like to do this is g plus kv squared with a minus 1 dt on this side. We have an inverse tan. Is that even right? What have I done? It wants maximum height. Do we really care about the velocity at a particular time? I don't think so. I think this was actually a wrong approach. We're going to start again, except this time with v dv dx. After all, we want to find how far it's traveled when velocity reaches 0. So let's do that again. Okay, going for the log. We checked, right? We looked at the question and realized they wanted a log, so it was clearly not the first approach. We want a k, 2kv, so we're going to 1 on 2k on the front. And because we're treating up as positive, hopefully this is not going to cause any negative sign issues here, and we have minus x plus c. When v equals to v0, x equals to 0 because it hasn't traveled anywhere. So let's just sub that in. Okay, great. I think minusing it over, and I'm seeing this, and I think they actually prefer to get x to the other side. So they moved x to the left-hand side and put that over to this side, where c is now over here. So we have 1 on 2k ln of g plus kv0 squared over g plus kv squared. Okay, great. And now we want at v equals 0, because that's when it reaches the top of its motion. And that's as required. At this point, I don't really think they nitpick about whether you write absolute values or not. So that's part 1. Now, when the particle lands on the ground, where is the ground? The origin is the ground, okay? Its speed v is v1, less than the magnitude of the terminal velocity. That doesn't look very fun. Like, this is a very standard question. I think you just have to churn through the algebra. If you've done any of the old syllabus papers, you would have seen plenty of these questions. So on the way down, we have two forces. We have the resistance force going upwards now, as well as the acceleration going downwards. Now what we're going to do is we're going to treat down as positive. So therefore A is going to be positive g minus kv squared. I'm not going to write the F net again. In this one, it seems like when the projectile lands on the ground, that means we probably should use v dv dx again. Yeah, okay. Because we don't really want to know when it hits the ground or the time it takes to reach the ground. We just want to know the speed when it reaches the ground. It's a kind of a tedious, non-elegant question, but these are questions that, in my opinion, are really accessible for everybody, and something that is worth attempting if you find a lot of the new syllabus content to be difficult to access. We have minus 2k, minus 1 on 2k at the front there, and Yeah, that's a 1. So we got x plus c over here, minus 1 on 2k, ln absolute value of g minus kv squared. Now remember, this is just on the way down, so we're going to assume that x is just 0 again. So when x equals 0, v actually equals 0. Okay, it's kind of important. So we have c equals to minus 1 on 2k ln g, because this is when it sort of reaches the top and is about to start falling down. We're going to do this. So let's quickly put that in. We have x equals, and c is that number. We're going to bring it to that side. Put a giant bracket in. Okay, I've obviously done the log law to save some time. Here, we want to know when x downward on the way down has traveled 1 on 2k ln k v0 squared plus g on g. So we're just going to sub this into that. Let's see what happens. Let's stick to the absolute value. I'm a bit scared about this particular thing going on because I think I've done something awfully wrong, but we just have to go with it. I think everything seems to be okay so far. Let's just add it to the other side. Huh. V1 is less than the magnitude. Oh, okay, so let's pick this as V1. Sorry. I'm gonna add V1 in there. So basically this just needs to equals 1. And I think we do have that. I think we have that actually happening. We just have to check, I guess, expand it and check. Yeah, trust. Let's go. So got k g v0 squared. Oh boy. Expanding minus k squared v0 squared v1 squared. Plus g squared minus kg v1 squared equals 1. No, yeah, and that's all over g, so we can multiply the g squared to the other side and cancel out that g, and we have, I'm gonna go kg v0 squared minus kg v1 squared equals to k squared v0 squared v1 squared, and dividing both sides by k, we have what we want. I don't know, I mean, I find this topic very tedious. There's no insight in this. You just churn through the algebra and get that out. The only thing I'm a bit concerned about here is the fact that they're talking about something about the terminal velocity, and honestly, for the amount of work we had to do, I'm not really sure why they mention a terminal velocity. I think it's got to do with the fact that on the way down, if the particle reaches terminal velocity, then V1 will have reached like some sort of limiting value and exceeded that limiting value, or equal to that limiting value, and what that means that it won't sort of have that same smooth ascent as it did on the descent, and it will reach the constant speed. And that, I think, might affect something about how on the way down like, I mean, x can be anything. If you reach terminal velocity, like x could be infinitely large and v will be the same thing, right? So I think that's why. But I do not think that you need to write any reasoning to argue about v1 being the terminal velocity or not. But I do appreciate that they've added this contingency, like this little clause in, because I think someone in the marking or exam committee has spotted the issue with this. But if you're falling the same distance down as you've risen, like it's highly unlikely that you'll reach terminal velocity on the way down. You'll have to like go down a lot further, and in that situation, there's no way we're going to get this equality anyway. So moving on. 15. This is all the fun starts, and we've only got how long? An hour and 10 minutes. Goodness me. Okay. Well, let's hope we can spot all the answers, hey? Question 15. 15A, part 1. What I'm going to do is I'm going to try my best to, do things efficiently. So part 1 is a quick reduction formula question. We've got Jn equals to the integral from 0 to pi on 2 of sine n theta to the n theta, okay? And I'm sure that all they want you to do is just integrate. So this is a definite giveaway question where n is greater than or equals 0. I'm going to do this really quickly. We're gonna turn that into sine n minus 1 theta sine theta. Okay, so that equals to we're going to use that as v dash and that as u. This is actually the first time in this paper we had to do integration by parts. So for all the people that did Coronius 100 and all that, kind of like over-invested in this. There's a lot of negative signs here. You got to be careful. And another cos. Putting pi on 2 in, we get a 0. Putting 0 in, we get a 0. And the negative cancels out. We got 0 to pi on 2 of, we've got an n minus 1 on the front. We should move it to the front. And here we have a cos squared theta, which we are actually promptly going to turn into 1 minus sine squared theta. In close bracket, sine to the n minus 2 theta, d theta. We did not have to integrate this again. And that here is sine and another sine to the n theta. Now if you wrote this out, we have basically Jn equals to this with an n minus 1 bracketed by a j n minus 2 minus an n minus 1 of a j n again. So moving that to the other side, we have a jn 1 plus n minus 1, n minus 1, jn minus 2, and that's going really well. Jn equals to n minus 1 over n jn minus 2. Okay, fantastic. And I think for the greater than 2 thing is just so that we don't get a negative, so we can just like copy what they said and not have to think about it anymore. That's 3 marks. Part 2. Okay, let this, using the substitution or otherwise. So this is actually a really good thing. So they've given you some hints. They're going to call in equals to 0 to 1 of x to the n 1 minus x in brackets to the n, and they provided you with a substitution. So they're going to get let x equals to sine squared theta. Right, we're going to quickly work out dx. dx equals to 2 sine theta cos theta. When x equals to 1, theta equals to pi on 2. Just use the principal angle. X equals 0, theta equals 0, and you got those values. Okay, so we got 0 to pi on 2, x to the n. So we got sine to the 2n theta, and here we've got 1 minus x, which is 1 minus sine squared, which is cos to the 2n theta. Okay, well, who knows what this is going to be? Oh wait, and we haven't remembered to put in sine squared there. No, not sine squared, sorry, 2 sine theta cos theta. D theta. All this is looking awfully messy to me. 0 to pi on 2, we're going to tidy it up a little bit. We have a 2 at the front, sine of 2n plus 1 theta, and cos also of 2n plus 1 theta. This is very interesting, and I'm seeing where you can see where this is going, right? When there's an equal number of powers up here and up here, chances are they want to use 2 sine theta cos theta in some sort of terrible way to make sine 2 theta. Okay, so it's double angle formula, but just taken to quite an extreme. And yes, I can just looking at the question, that's where they're going with this. So what we're going to do is we're going to say, we're going to bring the 2 outside because it's sort of in the way. And we are able to go from 0 to pi on 2. And here, every single sine theta, cos theta, right, to the power of 2n plus 1, each of one of these is really sine 2 theta over 2. And by bringing it, like, taking it to the power, we can go 2 out and put 2 to the 2n plus 1 outside and go from 0 to pi on 2 of sine to the 2n plus 1 of 2 theta, d theta. Okay, so that's what's really going on. You're using the double angle formula and simplifying the stuff at the front, 2 to the 2n, 0 to pi on 2, sine to the 2n plus 1, 2 theta. And that's what they wanted. Except they didn't really use 2 theta. Whoa. Am I seeing a typo here? Whoa, wait. Have I missed something? Using the substitution from 0 to pi on 2, when did that 2 disappear? Oh, is this a first? Have we found a mistake in NASA HSC? Oh my goodness. Or am I cooking? Let him cook. Oh my goodness. This is React content. Oh my goodness. But the paper said just the same thing, but they didn't. Where did this 2 go? We're just going to continue, and my goodness. Okay. I must be delirious. I might have made a terrible algebra mistake and I haven't seen it, but surely. Okay. We'll just roll with it. Let's continue. We try to finish the exam in the allocated time. Hence or otherwise show that that in equals to. Look, frankly, I think we can just use their thing. So we know that Jn is this, right? And we can just using part 1. We know that yeah, we can just use Jn. Okay. I mean, I think we got to be careful here though. I'm just going to check something. They definitely dropped the 2. They dropped the 2. No way. Part 3 was going to be fine, but they dropped the 2. Oh my goodness. Has no one proofread this? Oh boy. Okay, so what we've got here is we've got the fact that 0 to pi on 2 of sine to the n theta, d theta, equals to n minus 1 on n of integral from 0 to pi on 2 of sine to the n minus 2 d theta, d theta. I'm catching the bug as well. Okay. Now, if we wanted to make some adjustments to this equation, so we have a 2 theta, the same thing should work. The only thing you need to do is, if you wanted a 2 theta here, you need a 2 theta there, right? Which means we need to put a half outside and to deserve putting a 2 theta there. And then we can artificially add a 2 theta there, but I'm feeling awkward trying to use part 1. I'm kind of not vibing it. And then we also need to turn this n into a n plus 1, which means that becomes n plus 1 and that becomes n plus. Let's just give it a go. We're gonna just have a go at turning all of these things into their appropriate things we changed. Okay, so we have a half 2 theta. I'm just worried about 2 theta. Let theta equals to 2x maybe, and therefore d theta equals to 2 dx. Yeah, I'm just trying to convince myself that I'm allowed to do all these substitutions. So should we have a 2 at the front or a half at the front? Now I'm confused. I'm sort of like, I'm tempted to just do the integration all over again. You know what? Let's just wing it. Because if you mess around with this, shouldn't you also mess around with the limits? Unless they're doing something really naughty there. I'm going back to this. Something went badly here. X equals to 2 theta. So if we made a substitution, we would have changed all the limits as well. That's what we have to do, right? So when x equals to pi on 2, theta equals to pi on 4. You can't do this. You can't just chuck this out for a dummy variable. That's not gonna fly. So I'm gonna use their part 2 because this approach is not working for me, and I'm gonna have to play around with it in the future. Okay, I'm gonna actually go back and try this part just in the form that they have left us. It's not like it's going to take a long time to do the integration. I'm just concerned why they're offering 2 more marks to do the exact same work as before. I can see where the 2n plus 2n is coming from. What am I writing here? 2n sine to the power of 2n minus 1 theta times by cos theta. Okay, sure. And that all is 0 minus 1 on I mean, earlier, 10 minutes ago, I was happily just substituting in like what they told me to, and now I'm sort of really bogged down. And we've got the other one. Now just note that that is going to be a plus 1. So theta d theta, like this part here is another in, just exactly in, and this part is, you got to be careful because that's actually an n minus 1, because when you sub in n minus 1 it actually makes the power to n minus 1. So and here is in as well, so we'll just bring that to the other side. We don't what's going on? I've completely bricked the question now. I'm actually struggling with this part here, because something just I must have forgotten something along the way. Yeah, because of the tilt factor. We're gonna salvage it. That 2n belongs here. No, not there. Okay, and that 2n continues to stick around for a long time. Yep. We're going to take our time with this. Something's still not quite right about this. I'm not getting what they're getting. I am missing a 2. Why is that? Why do you think I am missing a 2? Is that because in the earlier question, we should have had a 2 there, right? And a 2 there, and a 2 there, and a half there from the integration, and a half there, and more 2's everywhere, a 2 there, and a 2 there, and that means when we differentiated this, we get another 2 coming out the front. Okay, I'm ready to move on. I got really bogged down by this otherwise, like really familiar topic of integration by parts reduction formula. There's something terrible about this. I'm willing to move on just because I am running low on time. I have an hour and I really want to reach question 16. I'm not getting there. So I want to get to question 16, guys. So let's go to 15b. Okay, let's go. Let's just really need to change tack here. On the triangular pyramid, we're going to go back to the diagrams. Okay. Triangular pyramid, L is the midpoint of one of the bases, edges. M is the midpoint of AC. Oh, okay, interesting. So there's a lot of equal length here. Okay, so AC is the other base. That's crazy. Okay, and N is the midpoint of AD. So it's almost like everything's sort of going out this way. Yeah, and AC is sort of in the background, and N and L are in the foreground. Okay, and P is the midpoint of CD, and Q is the midpoint. I can't barely see any of this. Okay, all right, okay. And I can no longer judge if all of this is skew, and of course it's skew lines, right? Skew lines everywhere. Great, okay, that's really nice to see. And let B be AB, and C be AC, and D be AD. So all these things are coming. Look, to me, this just looks like another parallelogram style question where it's just in 3D. Show that LP. So to me, the way to engage LP is we can go from AL, and LP can be reached by going LA to AN. Should we go all the way there? Let's just check something. I want to use AB and I want to use AD, but only half of it. And then AC. That's hurtful. That hurts my brain just thinking about this. Yeah. Okay, and we can go all the way up there and get to DP. Okay. AD, then DP. LA is sort of there already because it's half of AB, so at least we got minus B. We got half C and D. I mean, I know where this is going, but why? Why do they do this? Yeah, okay. I want to go there, followed by there, because we know that this is half the vector AC. Like NP, because N is the midpoint of AD and P is the midpoint of DC, we know that this is half of the vector AC. I'm sure that will help. Yeah, I think that should be fine. Yeah, I think we have everything. So that 1 mark is not the worst. But that is awful diagram, I have to say. So we say that LP equals to LA plus AN. We don't want to use the entire AD, so we're going to go to AN plus NP. But we know that NP by virtue of a 2D diagram, we can convince the marker that we can tell MP is half of it by similar triangles or some kind of thing, you know. And I don't really know when it comes to vectors how much reasoning is needed to prove that MP is half of AC. I think it's just intuitive. And up there is D. So we're just taking that particular plane of the triangle ADC, even though AC is so confusingly drawn as a dotted line, so you know, because it's in the background, that's actually what happens. Okay, so there's MP. So we got LA, which is negative a half of B, plus AN, which is a half of AD, which is D, and a half of AC, which is just C, and that's fine. Okay, part 2. Sorry, I just need to go back to my working out, isn't it? Okay, part 2. They provided a bunch of other things because they obviously found LP and MQ. Where is MQ? Another of the skewed lines joining them, and the proof. What? Okay. We're going to say that these are of a very similar proof to this. I'm just staring a little bit at this particular problem here, and I just think, why? AB. Okay. Plus this equals this, and this reminds me of that, you know, like those times where you probably think, yeah, they want us to times all these 3 things together because that's what the cool kids do. But why? Now, one thing that I think people are becoming more and more aware of, at least this is what we train our Extension 1 kids to do, is that when you see something like this, and you have a vector expression consisting of all these other things, you're going to be tunnel vision into doing this. You're going to be doing LP, dot LP, like dot itself, like this, right? And you're going to be doing that for all these other expressions too. And then with the hope that if you were to expand this dot itself, you can cancel out all the terms and get exactly what you need. And I think that's exactly what's going to happen. So we're going to write it out. This is actually one of the easier 3 marks you can get. And I would say that without getting sort of bedazzled by this diagram, it becomes an algebraic vector problem. Vectors are such a fraught topic where I think with some tricks, you actually take a lot away from it's an algebraic gimmick of a chapter rather than a meaningful geometry of a chapter. The only time we've assessed vectors in this exam so far is a very easy vector equation of a line question earlier on. So let's look at the right hand side. We have 4 bracket, and I'm just going to straight away convert this to LP, dot LP. We are about to sub everything in. And R. Okay, and here we have 4. We just have a lot of dot producting going on. We have a half times a half. That's a rule about dot products that can be used. A half times a half, and we have minus B plus C plus D dot itself plus all the other fun that we're going to have. So assuming that all these like the factors, sorry, I'm going on the wrong page again. I need to remember. I'm just getting too engrossed in this exam. And we are just going to expand this. Okay, so what we're going to have is we're going to have B dot B minus, we're going to do the terms first. We also have minus 2 B dot C minus 2 B dot D. We're just going through the motions. This is where you get to mentally take a break. That's the first 2. This is the LP dot LP. The second part of this is you've also got B dot B, C dot C, D dot D, and minus 2 again. I'm a bit worried about that, the fact that there's another B, what's it called, B dot C there, that's a minus. That's not a good look. Hope it works out. Okay. And then we have the other pair of minuses, the 2C dot D. And we also have a plus 2B dot D. This is MQ. And last line we have B dot B, C dot C, D dot D. This is pretty. So we got minus 2 B dot D, minus 2 C dot D, and this was NR. And you're going to add all of that together. I'm a bit worried about the 3 here, but you know what we're going to do is I'm just thinking AB. Yeah, I mean, I kind of see where this is kind of going, but still a bit concerned. See, there's 2 negatives of each one and a positive, so 2 BCs happen twice, and also a plus 2 BC, so we're not getting a minus 2. What's the other combination? B dot D. This bothers me a bit. I think now, just going back to the question, I'm sort of vibing that we've got AB, AC, and AD, and there's too many of these. There's a few too many of these, which I'm concerned about. But also we have BC as well. What is BC? Okay, so what we can do now is focus on the left-hand side, because the left-hand side has a lot of stuff, right? The left-hand side equals to AB. Now I'm just going to call it, we're just going to have A dot A, or you know, magnitude of A, vector AB squared, plus B dot B plus C dot C. Now let's just do BC really carefully. BC is the subtraction of C and B. I can't believe they did this. Okay, so just as for the marker, and we're going to go BD. We'll use B here just to be consistent with the order of the question. And lastly, CD. And that would expand all into what exactly we want. So really, honestly, we'll just say dot 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 for the first one. I think by this point in your working, if you can show them this much ability to expand a perfect square, I think you know the marker understands. You understand each other. You have connected with the person marking your script. Honestly, like C dot C. And honestly, that is the right hand side. Okay, great. I'm keen on 16. I've got how long? I've got 40 minutes, and I'm not even up to question 16. Okay. Question 15C. All right, this is the spiral question. I have not thought about this since I began the paper, and at this point, I'm kind of tired. I honestly not sure what they're sort of searching for in this question. It says by using the diagram below, so it seems to give you this little diagram trick again, and initially at the point it moves along, so we know that it's starting from below and ends all the way out. The z value is clearly increasing at a linear rate, and the circularness is obviously going to end back somewhere. Okay, so graph of the functions. I'm considering the graph f of x, g of x. So which one's f of x? The cos graph. G of x is this graph. Why did they provide us with this? Give a possible that described a curve L. Okay, so f of x. Why is it starting from minus x equals minus 4? Yeah, okay. And how many times did it turn? Once. It turns at like, imagine if you were going around up in the circle, right? That, to me, that is one revolution. So I'm going to count it. 1, that's 1, 2, 3, 4. No, just a little bit before. Interesting. Oh, interesting. Okay. This is certainly new to me. I have not practiced this kind of thing at all in the past. What is happening here? How would you teach students to come up with something like this? Like a general sort of parametric form will be something that looks like this. When t equals 0, and you begin at oh man. I see where this is kind of going. I see where this is going. This reminds me of those good old days, you know, the volume topic, where like you got to look at it from a different direction. So just imagine. All right, I'm gonna give you some ideas here. So when z equals minus 3, this is the picture you get, and a dot of a circle. As z starts to become goes towards 0, you get a full circle. You get a nice big circle, which is, you know, got a radius of 3. When that's biggest the circle gets. And as z, question 9, the answer is D. Hey George, what's going on? Question 9, the answer is D. You reckon? I mean, like, I'm running out of time. I've got about 37 minutes to do the last part of 15 and try 16. And I gotta say, this is damn hard. I haven't actually done this topic before, so it's been a struggle. And also, for those of you who have tried the paper, is there a typo on 15A part 2 over here? Is there a typo here? Can someone like verify? Just so like, you know, unless I'm just cooking. Who knows? Okay, and I know that when z is all the way up at 3, it's back to a dot, and I think the width of this is related to this. So the radius of the circle is related to this curve, and it begins at a non-existent value at minus 3, and it kind of goes up. I'm guessing that's what's happening, but I'm just wondering. The particle is moving away from the origin. You reckon? 9 is D. Did I pick 9 as D? Yeah, I picked 9 as D. I picked 9 as D. No, definitely. 9 is definitely D. Agreed, Dom. For sure. I actually gave up on 10, and even then I'm running out of time to try and do the rest of the paper. this is not cool. And I'm kind of getting bogged down by this really open-ended question of 15C. I'm going to give it a shot just by writing a best case attempt. I'm not that confident on what this 15C is about. So the way I think about it is that Z has to go from -3 to 3. Okay, and as it's doing that, the radius of the circle in the middle, so the X and Y are going to be provided by some kind of radius multiplied by a cosine sine, but I am not 100% confident on what something t and y could be a changing radius but sine of something else t, like, because it does make a circle as it goes around. It's the radius of the circle that is constantly changing, and it changes according to the rule. It changes according to the rule of square root 9 minus something t squared. So this is the sorry, I should be on my iPad right now. This is my thought process so far. All right, and I think if we can make this work, I'm gonna say if t was -3, we're at the sort of going left part of the circle. I mean, I don't know what part of the circle we're at when t is -3. My best attempt at this point of question 15C is actually going to be this. I'm going to put t here, and t is going to be from -3 to 3. And as z, but you know, the problem with z is that should z be the one that's following a circle up? Yeah. Let's go like this. No, you can't do that. You can't put like this, because if you put this, then z will be 0 in the bottom, and you don't want that. Okay, no, we're going to put t there, and when z is -3, the radii of the circles follow this particular equation. And because it rotates 4 times, I'm going to use their equation, which is pi x, but I have a feeling this pi needs a bit of work. It says spirals 3 times around the sphere and with radius 3. Spirals 3 times. Now, if we have this thing here from -3 to 3, how many entire revolutions of this do we get? We'll be starting from -3. It's not like theirs. In their graph spirals 4 times. We will come back to 15C. This is we're now going to scrounge for marks. Look, it's been many years since I've attempted the HSC myself, and I don't think I'm as sharp as I used to be. And also having not done the syllabus, this is not easy. This requires some insight, and I think it probably is a good question. We're gonna come back to this. I'm gonna spend a quality, let's say, 30 minutes on question 16. This is quite hard. A 16. Okay. All right, we'll get some free marks from A part 1. Let W be the complex number. Yep, show that. Okay, so basically all we have to do is say W cubed equals to e to the 2 pi I, which equals 1. Therefore, W cubed minus 1 equals 0. W minus 1, 1 plus W, so equals to 0. Since W is not equals to 1, it satisfies the second bracket. Okay, so moving on, 16A part 2. Okay, part 2. Show that in the triangle. So we have vertices of a triangle, and we are presented in the complex number by A, B, and C. Okay. Yeah, sure, whatever. I think these are just like to do with these complex numbers that we found. Okay. If the triangle is anti-clockwise, okay, and equilateral, then this, what's A, B, and C? Are they saying unit triangle? Not even unit. Okay, so that's A, that's, what? What? Okay, so that's B minus A, that's C minus B, why am I writing vector form, and A minus C. Why? Why do they care about this? I mean, I kind of know why, but honestly though, really, they want us to do this? Okay. So this is what I think they want you to do. So in the anti-clockwise formation, we've got this situation going on. We're saying that this thing is the complex number subtraction of B minus A, kind of like vector subtraction from A to B, right? And from A to C, we have a equilateral triangle. Oh, I drew a curve. And this is C minus A. Sorry, C minus A. Yeah, C minus A. And we don't need vector notation because these are just complex numbers. We're basically saying that this is a pi on 3 transformation rotation anti-clockwise. So therefore, C minus A equals to omega times B minus A. And let's just hope for the best because they have the same, they're equilateral. So does this work? Well, it should because we know this. So C minus A equals to WB minus AW. But they want CW squared. CW squared, and they also want BW. We have that already. We do not have CW squared, and we want to do away with the A's. So how do we make the A's disappear? Okay, let's have a look. C. Unless I've like done the order wrong. Surely. Triangle ABC is anti-clockwise. We need to make the C go away. Like, we need to make the C go away pronto. Yep. And we've also got this other one. This is like such a gimmick though. Like, I hate doing this kind of thing. I mean, you're really just trying to force it to happen. Why is the CW there still? That shouldn't be there. What is going on? Yeah, A is there now, that's good. I can't make some of this stuff go away. I must be missing something. Oh, that's painful. That is painful. Can't even get 16A part 2. If it's an equilateral triangle, I'm not seeing it. I can see part 3. Part 3 is really easy. So A, B, and C respectively. Oh no. Oh no, what am I thinking? Oh no. Of course that's wrong. This is not even it. It's not even it. This is like the square root of W. Course. Oh, okay. But then like, how do we do that then? Do we have to square it? I really hope not, because they don't square it. You know, one thing we can do is we don't want to be doing square root because that just makes life too hard, right? So what we can do is this. We can say that this angle, this is B minus A, for sure. And we can say that to this vector, which is C minus B. And we can say that if we butt C minus B up against here, that will be 2 pi on 3, which is what we want. So okay, fine, C minus B. Yeah, that'll work. I'm hopeful. Okay, have we got what they want? We have WB again. We probably should. I'm just really suspicious. How are they getting A? Should we use something else? I don't like this diagram, so I'm going to try another one. I'm going to try this one. And we're going to call this one oh, painful. So we're saying this is a rotation of 2 pi on 3. I'm sure the other one would have worked as well. I really hope this works because I'm sort of running low on steam here. Let's times everything by W. Yeah, no, we got it, guys. I mean, like, I don't know if I really like this question or not. Okay, and this term here is just going to be what's it called? According to the other thing, which is -1. That was kind of awful, because if you go with a different approach, it'll actually be really convoluted. Like if you went with this, it could be a mess, or because we got multiple B's and we didn't want multiple B's. But I think if you timed everything by W, it could work out anyway. Like, yeah, like okay. Yeah, I'm sure it'll be fine. I'm sure it'll be fine. And this is not too crazy. Okay, so part 3. Now, if triangle is clockwise, ABC is clockwise and equilateral, so we got a clockwise version now. And equilateral. Great. And they give you another expression. Show that if this is an equilateral triangle, but they keep telling us it's equilateral. Like, why? Like, to me, this is simply a case of the sum. So we have, oh, but we can't do that, hey? Something's a bit dodgy about this. So far, Yeah, well that's not going to help because all you're going to get is equals 0. Oh, great. So clearly it wants you to use parts 2 as well. So you reckon question 10 is A? Yeah. I'm not sure if there's like a giant time delay in the stream. I wonder if there is a time delay. It's nuts. Okay, well let's have a go at trying to make this happen. ABC is anti-clockwise and you get this. So far we have okay, you got this thing. Show that if ABC is an equilateral triangle, then this is true. A squared plus B. Do not tell me this is another one of those situations where oh no. Are we really doing this? Oh no. No. Oh, well, we're not even writing the other terms, are we? I don't even know what I'm doing anymore. But like, there's an OR statement because we're using the other one as well. We know W cubed equals 1, so that's good at least. No, I'm not seeing it. Yeah, we might have to just drop the part 3, so later. See if we can salvage anything. We got a bunch of people saying disagreeing on question 10. Interesting. Question 16 part B. How are we going for time? We have a solid 20 minutes left for 16 part B. Prove that x is greater than ln x for x is greater than 0. I feel like something like this is kind of silly, because what you can do is to prove a graph is greater than 0, that you can simply do this. I mean, can you graph it? I don't know. Let's try this. But the problem with this is that sometimes it's actually quite negative. It doesn't work. Should we try a graph? You got x, you got ln x. For x is greater than 0. We want to prove that that this difference is always positive. And to prove it's always positive, we can attempt by proving that the gradient is always positive, but it's not. This gradient is never always positive. But what we can do is we can break up the proof into 2 parts, okay? So what we do is we say for x is between 0 and 1, we just have to improvise. We can say that ln x is less than 0 while x is greater than 0. Therefore, x is greater than ln x for x is between 0 and 1. And then we can say for x equals to 1, x equals 1, ln x equals 0. Therefore, x is greater than ln x for x equals to 1. Then we say for x is greater than 1, we have f dash of x is 1 on 1 minus 1 on x. And for x is greater than 1, this is certainly greater than 0. So it's always monotonic increasing. And we know that at x equals 1 as the boundary, x minus ln x equals to 1, which is already greater than 0. So when you have a graph that's already greater than 0 and it continues to increase, therefore f of x is greater than 0 for x is greater than 1. So we salvaged the question 16b part 1. Part 2. Using part 1 or otherwise, prove that for all positive integers n, each of that is that. Okay, so this is actually one of those really unscaffolded questions that someone with experience in the old syllabus can do quite well, I think, maybe, question mark. So it's known that x is greater than ln x. That's great. So the first thing we realize is that something about this sort of speaks to me like it's going to be like e n, left-hand side equals to e n plus 1. Okay, and then on the right hand side we've got that thing squared, which is interesting. How are you going to get that to happen? I think there's some sort of graphical insight that you need to find here to make this happen, and it's positive integers n. Positive integers n. Let me think about how this happens. I'm kind of seeing it. I'm kind of. Oh, hey Carrots, how you doing, mate? How good is the YouTube response time? I've never really used YouTube Live before. I wrote Carrots just now. Tell me if you see Carrots on the screen there. Yeah, but honestly, like I'm trying 16b part 2. I've given up on a couple of things along the way. I think I see a mistake on question 14 something. Is there a typo in the HSC on question on this one? 15a part 2. Is there a typo there? There should be a 2 there. You know, I'm not sure. Like in the middle of an exam conditions, you're trying to do the exam, it's quite hard to be that confident that there is a mistake somewhere. But I'm sort of having a think about this 16 here. I'm nearly out of time. I've got about 15 minutes, and I'm definitely no state rankings from this teacher doing this exam. It's not an easy exam at all. Okay, and I'm sort of trying to use B part 1 of 16 to do B part 2. Like what I have found is that if you interpret this in a certain way, like this, for example, there is something awfully, you know, like my senses, my spider senses are telling me that this is the sum. Yes. Oh, this is the sum of an AP. Like this is sometimes, you know, when you see something like this in an exam situation, you are very satisfied. That is the sum of AP. Do you know what this is, guys? This is like, I know that n plus 1, right? It is this thing on 2. That. Because we see this all the time. This is what's going on. And why do we want this? Because something about n factorial really speaks to us. You know, we know that this is bigger than ln1 plus ln2 because we just proven that damn thing. Oh, that is very, very testing of people. Okay, and therefore we know that this is pretty much the answer. Yeah. Wow. There was no need to do rectangles like we thought it was going to be. Like I was about to start going, oh, you know, maybe it's like this thing, and then like we go, oh, but this thing's higher than this thing, and then all that. No, that's not needed because you basically just use this really obvious fact. That's what part 1 is to help you to do, and then so you go e to the on 2, which is just a square root sign, right? It's just to the power of a half, is greater than ln of n factorial, and then you just square the other side, and away we go. Everything's positive anyway, so that's fine. That is disgusting. I do have to say, like, that already should be a last question. This used to be the difficulty of last questions in the old HSC. So they put it at the second last, so something's going on in the last one. We're going to have a final push. We've got about 10 minutes exactly for the last 3 marks. The complex numbers both have modulus 1. Lovely, just like last year, hey? And the argument of, okay, so we got this little situation here. Now, the way I'm sort of already thinking about this, I'm going, yeah, that means ZW, like if that's W and that's Z, it's an obtuse angle with Z being further anti-clockwise. Something like this, right, is happening. Okay, where argument to principal argument. So I know that there is probably some complications when you do the principal argument, like, you know, but let's just say it's this. Okay, for real numbers, consider the complex. What? Why would they have a denominator of Z on the? Oh no. No, why? So you got real things multiplied onto this. Clearly sketch the region that contains all the points x, y for which. Great. Hey Zar, how you going, man? Just about to. I'm about to wrap up. I've got about how long left? Not sure you can see the time. I have to end at that time. I've got less than 9 minutes, and I'm nowhere near seeing the point of question 16C. And I've dropped marks along the way as well, including multiple choice question 10. So on the xy plane, we have this thing where they want the argument of this to be between pi on 2 to pi. xy, why? Why do they do this, and why is it over z? This is very suspicious. I'm sort of thinking that they intentionally put it like this to mess with you, right? There is something really dodgy about this particular fraction, because why not have it like this? Not W, Z. Okay. And what do they want out of this? They want the argument of this between 0 and... I can't geometrically visualize this in light of that. Why do they do that? Now, if you were like sort of the previous question looks like it wanted to get a different result, by the way. You reckon? This one? You mean part B, part 2? Are you referring to 16B part 2? Because I think I'm happy with that one. Oh, thanks there. Look, I eat both sides, but I forgot to delete the ln because I actually eat both sides. Okay, that kills the ln. Good one. Good spot. Good spot. I don't know. I feel like the marker, seeing what I've done here, you know what? They're going to be rude, aren't they? They're going to give me like 2 out of 3. Like that's a cardinal like mistake. That's terrible. That's terrible. Especially considering that you're elated in actually getting the question out. Like, I mean, I was so excited about seeing it that I didn't e to the ln. My bad. Okay. Oh, how funny. Cheers, mate. Cheers. Okay. Now, last ditch effort on this final question there, where we know that x and y are meant to extend, right? They're sort of just scalar multiples, and addition is going to provide us with some kind of like parallelogram pointing out into the space, sort of in that zone there, assuming that we have this kind of obtuse angle situation. And dividing by z makes it quite hard to achieve, because if you try to divide by z, then what will happen is that, like, how do you get something of obtuse angle? Like, let's say we had this zone, this entire section here. How do we get an obtuse angle? We could have an obtuse angle by pointing it that way, by making x, no, the one in front of z, yeah, by making x negative. That's one way to do it. So if y is positive and x is negative, no, but that screws up the addition. That screws it up, so if it goes over here, that will be the sum. Okay, if x is negative, let's say we had this combination. The parallelogram will go over there, and that's acute. That's acute. That's not good. We can't have that. Oh, goodness. Okay, experiment a little bit more. Let's take a more specific case. I want something where z is extreme and w are extremely like different. So maybe like this, and they're both modulus 1. So they're both 1. Okay. Let's say we made this and just kept them both as 1. We get the rhombus. Got this rhombus there. That over that it's not gonna work. Okay, so let's say we decided not to go there, but make it shorter, like this. So this parallelogram. And that parallelogram is still not going to play well with z because it's in the wrong direction, because you want it to be between pi and 2 and pi. Okay, so what about both of them being negative? How are we going for time? About 3 minutes left. Oof. Okay. Let's say we went that way, and we went that way, and we just have a little bit of this, so that the expression that we got on the numerator is actually this vector, this vector. This is the vector, and z is that vector. Why am I using a rubber? Oh, what am I thinking about? Like, what we really want, guys, we really want this quadrant. This quadrant is achieved by x. Yeah. No, I think this is our best effort here, because to once we get into this quadrant, you know, if we just think of what's it called, w and z as sort of like the two sort of arms making a number plane. This is like your number plane now, right? This is number plane. Then what will happen is that you've got like 4 quadrants, like 4 sections. 1, 2, 3, and 4. And in order for the argument to go from z into an obtuse angle, you want to target this quadrant. And if you want to target this quadrant, both x must be less than 0 and y must be less than 0, because you want to get inside of this, right? And that means the answer to 16 part C is this. the third quadrant for X and Y. And I think that's my attempt for 16C. So we're about 1 minute left. I want to take a quick dive at question 10. We can always make a guess at question 10. What's the guess going to be? There's no way we're going to, like, how do you process that in inside of 1 minute? I want to pick the viewer response. Should we pick Dom's answer or TY Web 5550 answer? I want to pick TY Web because TY Web wants to contradict Dom, and we're gonna go for a B because that's what he said. Okay, so that's the end. So, and this is where the invigilators go, oh, everyone pens down, and I'll probably be very disappointed with myself because I'll tell you how many marks I dropped here in this exam. So, in this exam that we've attempted, we dropped question 10. So I'm just going to make a list of lost marks. We lost question 10 completely. That was just unfortunate. It was a decision I made earlier in the 3 hours because I knew that this was going to eat up a lot more time than it deserved, and it's just something we couldn't do. The paper went along happily, and everything went sort of well. I started getting bogged down just writing stuff up at about end of 13. So this question in the second half of 13 is something that, setting out wise, I'm not familiar with. I didn't know that in the new curriculum, in the new syllabus, you can have integration involving the two different components and how much work is involved, because this one is a separable differential equation for both velocity component X, velocity component Y. That's a lot of work for 3 marks just to get to this. Is that the trend of the new syllabus? Maybe, right? And cheers, George, you're still hanging out. And once we got to question 14, I was happy. I got out everything in 14, but a lot of writing involved in these resisted motion, and and the two collision. We spotted the correct answer and made a change to our answer. When we got here, this one, I'm going to type a response in the Board of Studies forum entry. I just think something's wrong with 15A part 2. Is that a typo? And if it is, I don't know, it's not the worst thing that has happened in the Board of Studies or NESA. This question ended up being extremely tedious because you had to do left-hand side and right-hand side, but we managed it, in the time of the exam. It took a lot. No, this was okay. These were okay. There was another one later that was annoying. 15C is something that I'm utterly unfamiliar and uncomfortable with. So 15C, we would have lost anywhere between 0 to 3 marks. So question 15C, we have we would have lost 1 to 3 marks, or 0 to 3, probably 1 to 3. I don't think I can get full marks for this. Okay, and over here, this managed to come out after a little bit of fiddling around and choosing the correct combination of 120-degree rotation, choosing this going that way and that going that way so that we can get a 120 rotation. So that was okay. I could not do 16A part 3. That was a 2 marks there. Okay, that took, I decided that it was something I would think about later because I couldn't see it. Okay, so that's 2 marks there that I just can't see it at all. And lastly, we were very proud, although a viewer, it's not the whole quadrant. So I wasn't that confident that it's the whole answer either, Taiweb. I was happy with B, although I could have lost 1 if the viewer didn't tell me. So 16B, there was a silly error. Maybe lost 1 mark. And 16C, I'm not sure what kind of marks I'll get for the final last-ditch effort on choosing the quadrant, because as Ty Webb said, there's probably more to consider. They're not just going to award 3 marks for finding a quadrant. But I thought I had the idea, so I'll hopefully just get 1 mark for it. So I could lose anywhere between 1 to 2 marks for it. Hopefully not all 3. Yeah. So overall, as a summary, this is what a teacher, currently teaching just Extension 1 courses in the state is scoring, and this is assuming everything else gets marked correct and perfectly. We only managed to get a range. The best case scenario is probably losing 1, 2, 3, 4, 5. Best case scenario is 95, and that's being very optimistic about the sphere one. And the worst case scenario is probably 1, 2, 3, 4, 5, 6, 7, 8, 9. So probably 90 to 91. I don't know. I really think there are really strong students out there in today's HSC that can get better than that and get the state rankings. I think 95 might not even get the state ranking, given how strong some of the candidates are in the selective schools. But yeah, that's quite humbling, right? I think often as teachers, we over the years become better at teaching and not as good as doing this under exam conditions. I mean, of course, I can talk tons of cope and be like, oh, I've been talking the whole time through the exam, and I probably could do this faster if I was doing it by myself. But hey, at the end of the day, if you're put in the shoes of a student with all the pressure, like questions like the factorial one is really hard to see under pressure, even though it's so elegant. But yeah, thanks for everyone for watching, and this has been a really fun experience, and hopefully, if I get a chance down the track, I might, correct my answers and put a much better written iPad version on the links in the in whatever the YouTube video product ends up being. Yeah, I appreciate anyone who's dropped by, and I really hope you guys have the best of HSC exam attempts in the next couple of weeks. All the best, everyone.